Auzubillahiminash-shaytanir-rajim. Bismillahir-Rahmanir-Rahim. I dedicate this work to my beloved father Syed Kazmi, late siblings and the Ummah. My introduction: Syed Absar Kazmi from Pakistan and my rest of the particulars. I'm doing my masters from International Islamic University, Malaysia. A comprehensive presentation on photo detectors. Subject is semiconductor devices code and the lecturer is Dr. Fazlin Hasbullah. Outline, and these are the outline we are going to cover in this lecture: element periodic table, classification of optoelectronics, history of opto detectors, photo detection principle, modes of operation of optical detector, law of conservation and optical absorption, types of photo detectors with respect to p-n junction. We are going to discuss briefly about photodiode, pin photodiode, avalanche photodiode. A periodic table. In periodic table, our focus is in group 3, 4 and 5. As we know that group 3 is also known as a trivalent, group 4 is known as a pentavalent, and group 4 is regarding to totally semiconductor, but with the help of 3, 4 and 5 we can make compound semiconductors. Classification of optoelectronic semiconductor devices. Optoelectronic devices are classified in LEDs, photodetector, photocoupler, holograms. Our concern is within the photodetector. In photodetector, it is classified within two types: light conductive elements and photoelectromotive elements. And within a photoelectromotive elements, we are going to discuss about the p-n junction. The rest of two are NPN junction and photo ICs. But our main concentration will be in photodiode, pin photodiode and avalanche photodiode. History about photodetector. John N. Schiff was an American physicist and inventor who made a remarkable contribution in a solid state physics and electronics engineering during the early days of development transistor at the Bell Telephone Laboratories. He has done his graduation in physics and chemistry in 1934 and PhD in 1939. In 1948, the Schiff implicated light beam instead of a meter terminal as a wire for transistor, generating holes that flow via collector. Laterly, this device was appellated as phototransistor. This is his snap. What is a photodetector? Semiconductor device which can be implicated to detect the photon's presence. Such devices are known as a photodetector. They transform optical signal into electrical signal. When excess of electrons and the holes are generated in a semiconductor, response is proportional to power in the beam. These are some of the samples of the photodetector. Now the principle of photodetection. Photodetection principle is based on the two types of photoelectric effects, which are as follows. The first one is external photoelectric effect, in which electrons becomes free from the metal surface by energy absorption obtained by the stream of incident photons. Photomultiplier tube and vacuum photodiode are the implication of external photoelectric effect. The second one is internal photoelectric effect, in which free charge carriers are generated by absorption of incident photons in semiconductor junction detectors like PIN photodiode, PN junction photodiode, and Avalanche photodiode. Important detector properties are responsivity, spectral response, and rise time. Operation regimes of an illuminated junction. The first one is photo detector, which is operated in the third quadrant. You can see in the diagram. This is the pointed. This is shown that within the third quadrant it is operated, and the other one is a photovoltaic, which is normally a solar cells, is operated in the fourth quadrant. Modes of operation: photoconductive versus photovoltaic. A photodiode can be operated in two modes. The first one is a photoconductive, which is operated in the reverse bias. The photo detectors are operated in a photoconductive mode. The other one is a photovoltaic, which is operated at the zero bias. Likewise, solar cells are operated in the photovoltaic mode. This is an example of the photoconductive mode, and this is the example for the photovoltaic mode. You can see the supply is connected just to make it functional, and with the help of photons it will be operated. The photodiode implicated in the electrical energy generations are optimized to have a high efficiency of energy conversion. The photodiodes used as a photo detectors are optimized to have the fast response times. Photoconductive mode in brief. In photoconductive mode, the diode is operated in the reverse bias, which in turn dramatically reduce the response time at the expense of increased noise. Consequently, the faster response times can be achieved by increasing the depletion layer and decreasing the junction capacitance. The photocurrent is linearly proportional to the luminance for the given spectral distribution. Photovoltaic mode. In photovoltaic mode, this mode exploits the photovoltaic effect, which is the fundamental for the solar cells. When used in the zero bias or the photovoltaic mode, the flow of the photocurrent out of the device is restricted and a voltage built up. As far as the topic is concerned, we are focused on the photoconductive. You can see the characteristic curve for the operating modes. The photodiodes are operated in this quadrant, and the photovoltaic cells are operated in this quadrant. So this one, the operating mode for the photodiodes is photoconductive, and this one is the photovoltaic. Current voltage characteristic curve. In the current voltage characteristic curve, it is very obvious. You can see this graph, which is actually the zoom in from here. The luminance versus the dark current. Dark current is the minimum current without light, which is normally generated without light. When diode is in the reverse bias, a very minor current will flow, which is known as a dark current. So the reverse current which is produced is directly proportional to the luminance. You can see this one is a linear graph, which means as much as the light intensity will be increased, the reverse current will be increased. Light spectrum versus wavelength and the energy. This is the light spectrum. You can see the infrared, red, orange, green, all of the lights are here, which are visible, and the materials are also shown over here: silicon, gallium arsenide, silicon carbide, and all of the materials regarding this one. Correspondingly, This one is the wavelength corresponding to every material, as well as the energy gap in electronic volt, and the wavelength is mentioned in micrometers. So the response from the material from the red to the violet, at this point where they have mentioned full width half, maximum is -3 dB down, which will be having the maximum response. And if we are deviating toward right side or the left side, the response will be reduced. Momentum conservation law. Momentum conservation law ensure that only the vertical transition are allowed during the absorption and emission. The diagram you can see, this one is our for the absorption, and this one is for the emission. Valence band, this one is the conduction band. When the photon will receive the energy, the photon is incident on the material, so the electron from here will move toward the conduction band. The diagram depicts band-to-band absorption in a semiconductor. An electron from the valence band going to an acceptor causes a hole to be generated. Reverse process can also occur. The most imperative mechanism for the recombination and generation is the light emission and absorption respectively. However, our concern is in absorption only. Optical absorption in a semiconductor. Interaction in the semiconductor, as far as the device are concerned, and the band-to-band transitions, the photon absorption process of a photon scatters an electron in the valence band, causing the electron to go into the conduction band. These two processes are very obvious, important for the light detection. Electron-hole photo generation. Most modern photo detector operate on the basis of the internal photoelectric effect. The photo-excited electrons and holes remain within the material, increasing the electrical conductivity of the material in a semiconductor. Electrons-hole photo generation in the semiconductor. Absorbed photons generate free electron-hole pair. Transport of the free electrons and holes upon an electric field result a drift current. This one is valence band, this one is the conduction band. Electrons move from here to the conduction band while leaving the hole behind. Absorption coefficient of some direct and indirect semiconductors. For the direct gap materials, the absorption coefficient is very strong once the photon energy exceeds the band gap. For the indirect material, the absorption coefficient is smaller near the band edge, but once the photon energy is more than the direct gap, the absorption coefficient increases rapidly. In the graph you can see the absorption coefficient, which is centimeter inverse versus wavelength. This is x-axis is denoted by the wavelength in micrometers, and y-axis absorption coefficient, and opposite to the x-axis it's photon energy in electron volt. Absorption coefficient and photodiode materials. Absorption, photon absorption in direct and indirect band gap semiconductors. This one is an example for the direct band gap, where valence band and the conduction band are aligned to each other. Once it is subjected to the photon, the electron in the valence band will move to the conduction band while having energy more than this energy gap. And for the indirect band gap, the movement of electron, it will move from valence band to the conduction band, but release the phonon, which is the loss of energy. responsivity versus wavelength. In x-axis wavelength, in nanometers, in y-axis it's the responsivity. So these are the three materials which they have shown: silicon, indium gallium arsenide, and the germanium. The responsivity of the detector varies with the wavelength and is maximum at the particular wavelength for each material. Just like for this material, this is the maximum response. For this material, indium gallium arsenide, this is at this stage it's a maximum response. For the silicon, it's a maximum response at around 900. At the larger wavelength, the responsivity drops sharply because the photon don't have the enough energy to kick electrons from the valence to the conduction band, and it's around 1300 to 1500. And indium gallium arsenide is an excellent material for the maximum response. For the lower wavelength, responsivity also reduces because of the increased absorption. Now the significance of photodetectors. The parameter for the photodetectors, some of the imperative parameters of the photodetectors are as follows. Quantum efficiency, it is the ratio of primary electron hole pair created photon to photon incident on the diode materials. Detector responsivity, this is the ratio of output current to the input optical power, hence this is the efficiency of the device. The unit of the responsivity is ampere per watt, but we have discussed just before. Spectral response range, this is the range of the wavelength over which the device will operate. The spectral response refers to the curve of the detector responsivity as a function of the wavelength. Noise characteristics, the level of the noise produced in the device is critical to its operation at the low level of the input light. The next parameter is the response time. This is measure of how quickly the detector can respond to the variation of the input light intensity. And the next one is the rise time. The rise time is the time for the detector output current to change from 10% to 90% of its final value when the optic input power variation is a step. The last one is the gain. In avalanche photodiode, a more gain than a pin diode due to the effect of the impact ionization, as it is operated at a high electric field. Now, types of photodetectors, P-N junction. First one is a photodiode, next one is pin photodiode, the third one is avalanche photodiode. Some of the examples have been shown in the pic. Photodiode, photo means light and the diode means a device pertaining to electrodes. A photodiode is a light sensitive electronic device capable of converting light into a voltage or a current signal. It works on the principle of the photo generation. This is the symbol and this is the package for the photodiode. Photodiode equivalent circuit. The simplified photodiode equivalent model represents the key element. The irradiance is proportional to the current source, ID, which is in parallel with the diode in the figure. Performance is dependent upon the parasitic components RD and CD can play an imperative role. This one is the diode, this one is the current source, this one is the parallel capacitance, this one is the shunt resistance, which is the equivalent of the photodiode. Photodiode working. Working of the photodiode is based on the internal photoelectric effect. Free charge carrier are generated by the absorption of the incident photons in a semiconductor junction detector. The diode is connected in the reverse bias under an incident photon. Free charge carriers are created by the photon absorption. The pair of electron and hole generated by every single incident photon, these moving charges causes the current flow through an external circuit. This one is a photodiode connected to the reverse bias. This one is the load resistance. The reverse bias photodiode is under luminance, is representing the energy band gap diagram in the figure, which absorb in the junction via window. The absorbed energy raises a bound electron across the band gap from the valence to the conduction. This one is energy band gap diagram. This one is energy band difference, p-type material. This one is n-type material. This one is depletion layer from here until here. This one is phonon shown over here, which will produce hole and electron pair. An electron will move from valence band to the conduction band, and at this position all of the electrons are accumulated. At this position all of the holes are accumulated. As to assume it will be better to assume the electrons just like a ball. So it will be tend to move from left to right downward as a slope, and the holes will move from right toward left just like a balloon. So within the electric field, these electrons are accumulated and will become a drift current with the help of electric field. As I've discussed, the free hole is left in the valence to the conduction band. Under the electric field, the generated free charge carriers produce the drift current. Now pin diode. A pin diode with a white light dot near the intrinsic semiconductor region between a p-type semiconductor and the n-type semiconductor region. The p-type and n-type region are typically heavily doped because they are used for the ohmic contacts. So this one is shown the p-type material, intrinsic material, n-type material. This one is a structure for the pin diode, P material, I material, N material, and the light incident on the material. This one is a power supply connected within the reverse direction. Energy band diagram. This one is a descriptive energy band diagram. You can see here, once light is incident on the junction, electron hole pair will be generated, and under the electric field they are separated. The electron free charge carrier will move toward the N material and the hole will move toward the p-type material, and it will produce the drift current. In the absence of the battery or the electric source, the generated electron hole pair will be diffused by a recombining process. So you can see here, when photons are incident, the electron will move from valence band to the conduction band by leaving hole in the valence band. The generic operating parameters of a pin photodiode. Parameters are wavelength range, responsivity, dark current, rise time, bandwidth, and the bias voltage. Symbols for the relevant parameters, units, nanometer, ampere watt, nanoampere, nanosecond, gigahertz, and the voltage. So these are the ranges for these parameters. Now, avalanche photodiode. Avalanche photodiode are the high sensitive and a high speed semiconductor compared to the regular pin construction photodiode. Avalanche photodiode in an internal region where the electron multiplication occurs by application of an external reverse voltage, and the resultant gain in the output signal means that low light level can measured at a high speed. Incident photon create electron-hole pairs in the depletion layer of the silicon photodiode structure, and these move toward the respective p-n junction depending upon the electric field. You can see here, this one is the structure for the avalanche photodiode: p material, intrinsic material, p material, and material, and this one is our avalanche region. Describing avalanche photo detector construction and the current voltage characteristic curve with a highlighted circle depict avalanche region in figure below, operated with a much higher reverse bias. This allows each photo generated carriers to multiply by the avalanche breakdown. The effect is known as an impact ionization, resulting the internal gain within the photodiode, which increases the effect of the responsivity of the device. Silicon material, germanium and indium gallium arsenide, along with the wavelength, responsivity, dark current, and avalanche ranges are mentioned here, and the avalanche photodiode will be operated in this region. Significance of the photodiode. Photodiode are the unique among the light detectors. When illuminated, they generate an output which is proportional to the light level. Their characteristic and the feature can be summarized as follows: low cost, visible and near IR photodetector, excellent linearity in output photocurrent according to the light intensity, fast response times, available in the wide range of the packages, low noise, mechanically rigid yet compact and the lightweight, available as a dual quad or the linear array, usable with almost any visible or the near infrared light source such as LED or neon fluorescent, incandescent bulb, laser flame. Sources are the light, sunlight. Silicon photodiode are utilized in such diverse applications: spectroscopy, photography, analytical instrumentation, optical position sensors, beam alignment, surface characterization, laser range finders, optical communication, and the medical imaging instruments. Photodiode, the relation of the light in Islamization. It is he who made the sun a shining light and the moon a derived light and determined for its phases, that you may know the number of the years and account. Allah has not created this except in the truth. He details the signs for a people who have knowledge. Indeed, in the alternation of the night and the day, and what Allah has created in the heavens and earth are signs for the people who fear Allah. These are the references. Thank you.